Okay, our next topic is astrodynamics topic number 3, numerical techniques and tools. For orbital computation. So, of course, the computer is an invaluable tool for calculating orbits. There exists a lot of software packages. Some of them you even may have access to as Georgia Tech students, for example, like Satellite Toolkit or some other softwares where they will do a lot of these complicated orbital computations for you, and they'll account for things like aberrations, multiple bodies, et cetera, and some of these non-ideal effects. We are going to learn a simple technique for computing orbits, because I always like to cover this. Even though there are tools out there for doing these things, you have to be able to interpret the tools. You have to kind of know when they make sense, right? And furthermore, just the ability to discretize and analyze a differential equation is actually a very valuable skill for any graduate student, I think, especially in research. This probably will not be the last time that you encounter a problem like this. And so it's always good to kind of work through it and say, well, how would you actually solve this problem? Or a problem like this. So what we're going to do, I'm going to put down our differential equations, and I'll teach you how to discretize that system of differential equations. And you will actually use this as part of your first homework assignment. Now, your first homework assignment won't be due for a couple weeks, but I'll go ahead and give it to you now. What we'll do, your job is to go online and find a realistic satellite orbit. It may be a dead satellite. It could be something in the past, something in the future, something now, whatever. But you will have to simulate that orbit and then track its look angle across the sky from Atlanta or whatever relevant location that you would like to observe from. The only rules are the orbit cannot be circular and it must be inclined. Other than that, it's fair game. You can basically pick whatever satellite you want, write up a little paragraph about what is the satellite used for, why is it in this orbit, et cetera, what's the history of the satellite, and then simulate its sky track as from a vantage point or Atlanta. Or if you pick a satellite that doesn't really make sense to observe from Atlanta, that's okay too. Just pick a location that makes sense to observe it from, and then go ahead and simulate the sky track. So start thinking about that now. You won't really have the tools to complete that assignment until we cover look angles, which will probably be at the end of next week. But it's relatively straightforward, and I think you'll have some fun with it. It's always fun to learn about these types of things. So let's go ahead and put down our original system of equations. R hat double dot is equal to R theta dot squared minus Kepler's constant GMP, whatever the mass of the planet, your body that you're orbiting around, divided by R squared. And then the other equation, theta double dot equals minus 2R dot theta dot over R. Those were the two coupled dynamical equations that we started out with. Now, what would be, how many functions, how many variables of coordinates are we solving? Well, that's easy, 2, R and theta. What is the order of these differential equations? Remember that from your calculus class, the order? Well, if I take the derivative once, it's a first order equation. If I take a derivative twice. So this is really two coupled second order differential equations. Okay, so then, hopefully you recall when you took calculus that if you uniquely define some initial conditions, you can then figure out the solution. And you need enough initial conditions to pin down this system in phase space, right? If there are two variables and each appear in second order, then how many initial conditions do you need to pin down this system in phase space and to actually have a tractable solution come out? How many pieces of information? 4. One for each phase and one for each variable, and one for each order. So it doesn't really tell you anything if I just say, okay, here's something in at r and theta at this initial point in space. Tell me what it's going to orbit. There's an infinite number of orbits it could actually satisfy and actually have at a particular moment in time that r and theta. I need 2 more pieces of information, namely the theta component of velocity and the theta component of r velocity, the r component of velocity, in order to actually pin down a precise, unique orbit that comes out of this differential equation. So, with that in mind, we are going to need to start with 4 pieces of information. And the 4 that we should start with is an initial r and theta. Let's call it r naught and theta naught. And also, we'll have Vr naught and a V theta naught in meters per second to denote what the velocity is. And of course, we could also say Vr is equal to r times theta dot. Oh, excuse me, V theta is equal to r times theta dot. And Vr is really just equal to r dot in cylindrical coordinates. Now, here's the other thing that we have to keep in mind before we solve this on a computer. A computer can't do analog functions. You have to discretize this system. We have to sample it with respect to time and solve it for different points in time and kind of extrapolate the behavior in between. So how do we discretize a differential equation? Well, differential equations take derivatives, and we need to find a way to take the derivative discretely. And you've probably figured out how to do this before in some of your other classes. So for example, theta dot, what I'm going to do let's do it this way. Yeah. Theta dot, I'm going to put a little index here to denote which sample in time I'm going to estimate this for. And I'm going to pick a sample size. So somewhere I have to pick a delta t, a unit in time between my different samples of my values in my dynamic system that I increment and compute from one moment to the next. If I can do that, then I can approximate this derivative wherever I see it in my dynamical equations as theta sub n plus 1 minus theta sub n, whatever I started with whatever I ended, divided by delta t. And of course, when delta t becomes infinitely small, that's really the definition of a derivative. I'm observing the points closer and closer in time and looking at the slope. And likewise, I can do the same thing for r sub n. R sub n plus 1 minus r sub n over delta t. And then, of course, if I have a double derivative, then really that's just like taking the derivative of a derivative, right? I take my sample of r sub n dot divided by time. I take this, and I take the two differences. And I divide by delta t. And so, here it is. We've got I'm going to call this delta r sub n. And I'm going to call this delta theta sub n. And now I have a framework for giving myself some initial conditions, giving me a starting theta and r, and also a starting delta theta n and a delta r sub n. And I can relate that to velocity via my formulas. So for example, let's say theta 0 and r0 are my starting points. And then delta r0 is going to be my starting velocity, v sub r, times my time step. So let me put this in here too to keep the units right. So in other words, I know what my analog v sub r is, my continuous time velocity as a function of r. I multiply it by the time step I've chosen. That gives me an initial delta r0. Likewise, I can make an initial delta theta sub 0 by saying this is v theta initial condition. Let's put a 0 there to denote initial condition. And let's see, for v theta, I've got to divide by r naught and then multiply by delta t in order to get my initial increment for angle. Once I do this, now I have a system of 4 pieces of information that I can start with. And all I have to do is keep updating these pieces of information. So for time increment number 1, I'm going to start from these, and then I need 4 equations that give me the next estimates for r1, theta 1, delta r1, and delta theta 1. And then for the next delta t increment in time, I need those same set of equations should relate my r1, theta 1, delta r1, and delta theta 1 to my r2, theta 2, delta r2, and delta theta 2. So we're coming up with a set of difference equations to discretize this dynamic system. We actually already have the first set of equations. Let me go ahead and write the whole discrete system down so that you have it, and then we'll talk about it. So this is my algorithm. R at time sample n plus 1 is equal to r sub n, my previous sample, plus whatever my delta rn is. Well, that makes a lot of sense, right? If this is my starting point, and I know what my r velocity is, I just multiply it by delta t. That gives me my delta r sub n increment. And that's what I'm going to move to the next point as. Likewise, theta n plus 1 is going to be equal to theta n plus delta theta n. So these are all 4 pieces of information that I can get from an initial condition. I just keep marching them and marching them. However, I also have to update these 2 pieces of state information based on the dynamic system, the discretized differential equation over there. What is this one? This is going to be delta r sub n. So my velocity, my r velocity increment is going to be equal to the same thing it was on the previous time sample plus a discretized version of that a differential equation that in some ways looks nothing like the equation itself. It'll take a little bit of visual acrobatics to see where I got this. So okay, what's happening here? This delta r increment, essentially the r component of your velocity, is equal to the previous one plus this system here, which is really just a discretization of this up here. You can see it kind of takes that form. I got a delta theta sub n, and I'm squaring it. That's kind of like this over here. But then I have this weird r plus 1/2 delta r sub n. And this is a little correction factor due to the fact that we're taking in order to get the second derivative with respect to time, we're taking the derivative of a derivative. And when you discretize a system like that, you're basically saying, okay, I'm looking at the difference between these 2 points and the difference between these 2 points, and I'm looking at that difference in here. And of course, that difference is going to be halfway between one difference and the other difference, which is why you need this correction factor to get everything to work out right. And then finally, this last one is 2 delta r sub n delta theta sub n over r sub n plus 1/2 delta r sub n. And so here you have it. The devil is actually in the derivations. And I think I have an example problem online where you can actually just go through and derive this yourself and then verify where the terms came from. It's a good exercise to work through. But once you've codified the mathematics like this is a very trivial computer program to write. In fact, where are my aerospace guys? Raise your hand. Okay, good. You can use like your first homework, you have to program it. You have to do the calculations. I don't care what platform you use. You can use Mathematica. You can write it in C. You can use it MATLAB. For some reason, half of my aerospace engineers always try to program everything in Excel. Yeah. Oh, I can already tell which lab you're from or which lab you're not from by how much wincing you're doing at that thought. So. Interesting. So yeah, I actually had a student turn in like a 50,000 cell Excel sheet for this assignment once, and I mean, you can do it, and it was right. Yeah, he got full credit, but not the way I would have solved it. But right answers are the right answers, so I don't argue. I've learned not to argue over the years when a student gives me a right answer. So let's see here. Any questions so far? Pretty straightforward. Let me give some examples. Right now I'm going to switch over to the document camera because I brought some examples of some code. Let's see, the light is on. We'll go ahead. There we go. Here we go. Let's see, focus. Okay. There we go. Autofocus is working. So anyway, you can code this up, and as sort of a benchmark, to your code on your homework, there's a little example problem where you just simulate the circular or elliptical orbits based on initial conditions. You can actually test your code or reuse the solutions online, kind of tailor that code to your liking, how you want to do it, for the first part of your homework problem. But keep in mind that's only part of the problem. So here's the initial conditions. I've got an R of 42,000 kilometers from the Earth. So imagine the Earth is here. The Earth has a radius of 6,000 kilometers roughly, so it would take up about this much space. And I launch a satellite into what should be a circular orbit. So I fed it the initial conditions of the geostationary Earth orbit that we learned about last class period. 42,000 kilometers from the Earth. I just started it at 0, so it would be here along the x-axis. And you'll launch it this way. So the initial conditions are, well, it's circular, so there should be no r component of velocity. So you see that's 0. And I calculated using that formula. Remember the formula from yesterday? Square root of gmp over r is your theta velocity component. That came out to 3.1 kilometers per second, 3,100 meters per second for a geostationary Earth orbit satellite. And I launched it with that tangential velocity. And then I just let that set of differential equations do the work. And it traced out a beautiful circular orbit. And sure enough, 23 hours and 56 minutes later, it got back to the exact same point, confirming that this is essentially a geosynchronous Earth orbit. Now, many of you, when you go to do this exercise at home, will have something that looks like this. Here's your planet. You'll start your simulator, and you will get this. What is wrong? If you're using this technique to simulate the time progression of your orbit, what is likely wrong? Can anybody think of some culprits? Yes, that's usually exactly what it is. Remember, this is a discretized system of equations. It's not modeling the disturbances in between the samples. And so the smaller your delta t, the more accurate it's going to be. At some point, if you make your delta t so big, it's not even going to close up on itself. Now, there's a trade-off there, right? It takes a lot longer for really fine delta t's. For this type of differential equation system, a delta t step of about 5 seconds will work for pretty well for Earth orbits. It'll calculate it. Your computer will calculate the entire orbit in a matter of seconds, and it'll almost always close up reasonably. Okay, let's try another example. What does this look like? What happens if I give a weird set of coordinates, a skewed set of coordinates? 30,000 kilometers as my starting point over here. 0 degrees, I'll always start it on x, just because there's always rotational symmetry. I can always tilt it if I want to start it at a different angle. Without loss of generality. That's how you write that in the textbook, right? Without loss of generality, we can begin any orbit at theta equals to 0. And then look, I gave it a kind of a skewed set of initial velocities. Both the r and the theta component have different values. 1 kilometer per second in the r direction, that would be here, and 2 kilometers per second in the theta direction, that would be in that direction. And so you can see, not surprisingly, when I give any orbit with a non-zero v theta component, you're guaranteed to have something elliptical. And that's what we have in this case. It's a nice elliptical orbit. Here's another one. This is a highly eccentric orbit. Look what I did on this one. These are all actual homework problems, by the way, that I gave years ago for the class. So let's see, I started off at orbit of 6,000 kilometers. So let's pretend you're on the surface of the Earth. And let's also pretend that there's no air resistance, right? I launch at 8 kilometers per second v sub r and 1 kilometer per second v sub theta. So it's almost like heaving a projectile up in the air. You see it goes up and it goes down, sort of in the limit of very small initial velocities. We almost get what the Newtonian mechanics of Earth-based surface gravity would predict, right? Lobbing a projectile up in the air and it kind of falls with this parabolic trajectory if there were no air resistance. And of course your computer's dumb, right? It just keeps going. It says, I'm going to go all the way to 0, even though this is like, you would be in lava at that point. And of course, I'm always a stinker, right? Like, faculty always have fun with their students. I didn't teach this, when I gave this assignment, I didn't teach this, but I gave them these initial conditions. So look, you're roughly on the surface of the Earth. We're using Earth-based gravity. 12 kilometers per second is my initial R, and v sub r, and my v sub theta is just 1 kilometer per second. I gave a little bit of velocity in the v theta. And I get all these people coming to my office hours. They're saying, man, my orbit doesn't close up. Look, it just keeps on going. That's right, because it's not an orbit. I sneakily gave them an initial condition that was greater than the escape velocity for the planet. See, one of the nice things about gravitational potential is that you can impart enough energy to actually break orbit. It didn't have to work out that way, right? It could be a 1 over r to the higher power law or lower power law that didn't work out that way. But we live in this wonderful three-dimensional world that makes it so that you can actually send spacecraft outside of your planet. And so the escape velocity of a planetary system, v escape, is basically 2 times Kepler's constant over your starting initial r. Take the square root. Okay, any questions? So the goal will be to have some fun with this. Go home and play around. You can get started on a little code that horses around with orbits. And the nice thing is when you work through these dynamic equations, not only do you have the shape of the orbit, but you actually have the time evolution, which is a bit trickier to calculate. It's more than simple Kepler's laws. But by doing this, you can work through, and if you get your code running, when you learn about look angles next week, you'll be in good shape to finish off your homework in fine style, in fine fashion. Okay. Any questions before we go to the next topic? Yes, good.
So the differential equation in a continuous time.
Can you solve it in a continuous time? Not using any functions that you or I would be familiar with. There are some special functions that are kind of tabulated just for this type of application that you could use for it. But in terms of like transcendental functions, no. Divide the second equation by theta. Yet it's tricky because they're coupled in a peculiar way, right? Because there's also a theta dot here, and there's some cross dependencies for those. So you can, I think it would involve elliptic functions. It's easier to program the difference equations to calculate your orbital evolutions. Good question. Very good question. Anyone else?